Assalamualaikum warahmatullahi wabarakatuh. In this video, we will presenting about the effect of surface color on heat absorption rate for our diploma mini project FSG311. This project was conducted under the supervision of our supervisor, Madam Azliana binti Ramli. For this group project, the group members are Nur Alia Maisarah binti Abdul Aziz and Alisha Sofia binti Nasran Kamil. Solar radiation is one of the main sources of thermal energy on Earth. When solar radiation reaches a surface, part of it is reflected while the rest is absorbed. The absorbed radiation is then converted into heat, causing an increase in temperature. The amount of heat absorbed depends strongly on surface properties, especially surface color and finish. Dark surface tend to absorb more radiation, while light and reflective surface reflect a larger fraction of incoming energy. Therefore, this study aims to quantitatively investigate how variations in surface color and coating affect a material's ability to absorb radiant energy and convert it into heat under natural sunlight conditions.
The objectives of this study are clearly defined. First, demonstrate how the color of a surface affects its ability to absorb solar radiant energy and convert it into thermal energy. Second, to compare the rate of temperature increase among containers with different surface colors when they are exposed to the same solar radiation intensity. This objective allows us to link experimental results with theoretical principles of heat transfer. Based on heat transfer theory and previous studies, the hypothesis of this experiment is that darker and less reflective surfaces will absorb more solar radiation and reach higher temperatures, while lighter and metallic surfaces will absorb less heat and remain cooler under identical exposure conditions. For the literature review, we found that the effect of color on heat absorption rate shows that surface colors plays an important role in determining how much solar energy a material can absorb. This is described by albedo, which measures a surface reflectivity, ranging from 0 for total absorption to 1 for total reflection. Dark-colored materials like black have low albedo, absorb more solar radiation and heat up faster. As a result, these surfaces experience a higher temperature increase. In contrast, light-colored surfaces like white have high albedo, reflect more sunlight and remain cooler, leading to much smaller temperature rises. Experimental studies confirm that black surfaces reach the highest temperatures, whereas white surfaces stay the coolest under the same. Heat absorption is affected not only by surface color but also by the type of surface coating. The pigment composition and the physical structure of the paint determine how much solar radiation is absorbed or reflected. Metallic paints like silver and gold exhibit different behavior compared to standard matte paints because they consist of a transparent colored top layer and an underlying layer containing reflective metallic flakes. These flakes reflect a large portion of sunlight across the solar spectrum, giving metallic surfaces low solar absorptivity. As a result, metallic surfaces stay cooler than dark non-metallic surfaces under the same sunlight exposure.
Thermal radiation is a mode of heat transfer that occurs through the emission of electromagnetic waves due to an object's temperature and does not require a material medium. In fact, all objects above absolute zero emit thermal radiation, and the amount of energy emitted increases as temperature rises. The ability of a surface to emit this thermal radiation is described by its emissivity, which compares the radiation emitted by a real surface to that of an older black body at the same temperature. Emissivity depends on surface properties such as color, material, and surface finish. Generally, dark and matte surfaces have higher emissivity, while light color and polished metallic surfaces like silver and gold have lower emissivity due to their high reflectance, especially in the infrared region. Solar radiant energy consists of ultraviolet, visible, and near-infrared wavelengths, and it interacts with material surface through reflection and absorption. For opaque materials, the absorbed portion of solar radiation is converted into internal energy, which causes an increase in temperature. Surface color plays an important role in determining how much radiant energy is absorbed. Dark surfaces generally have lower reflectance and higher absorptivity, which results in faster heating rates compared to light-colored or reflective surface under the same radiation conditions. Experimental studies consistently show higher temperature increases for dark-colored surface, while light-colored and metallic surface absorb less heat. Additionally, differences in spectral reflectance, especially in the near-infrared region, explain variations in thermal behavior, even among surfaces with similar visible colors.
Lastly, the behavior of heat absorption and emission can be explained using Kirchhoff's law and the Stefan-Boltzmann law. Kirchhoff's law states that for a surface in thermal equilibrium, the absorptivity is equal to the emissivity. For opaque surfaces, All incoming radiation is either absorbed or reflected, meaning surfaces that absorb solar energy efficiently, like dark colors, also emit thermal radiation efficiently. According to the Stefan-Boltzmann law, the heat radiated by a surface is proportional to the fourth power of its absolute temperature. Therefore, surfaces continue heating until the absorbed solar energy is balanced by emitted thermal radiation. Darker surfaces, being more absorptive, must reach a higher equilibrium temperatures, which explains why they get this experiment. The materials are 8 metal cans. Each spray paints consist of black, white, blue, red, yellow, green, silver and gold, sunlight and water. While for the apparatus, we need a solarimeter, a 300 ml beaker and 8 thermometers. For the procedure, 8 identical metal containers were painted in different colors and filled with the same volume of water. Each container was fitted with a thermometer and exposed to direct sunlight for 1 hour. Temperature readings were recorded every 5 minutes. The experiment was repeated over 3 days and average values were used for analysis. Solar radiation intensity was monitored using a solarimeter. This slide shows the results of our experiment, including the average solar intensity and the average temperature change of different colored surfaces over time. The first graph shows the average solar intensity measured every 5 minutes during the 60-minute experiment. We can see that the solar intensity is not constant and fluctuates throughout the experiment. It increases and decreases at different times, reaching higher values around the middle of the experiment and lower values towards the end. This fluctuation is expected because the experiment was conducted outdoors under natural sunlight where cloud cover and environmental conditions can change. In the second graph, it shows the average temperature of water inside each container with different surface colors over 60 minutes. For all colors, the temperature increases with time, showing that solar radiation is absorbed and converted into heat. The black container shows the highest temperature increase throughout the experiment, indicating the highest heat absorption. In contrast, the white container shows the lowest temperature increase, meaning it reflects most of the incoming solar radiation. Metallic colors like silver and gold remain cooler than darker colors, even though they are not white. This happens because darker colors have higher absorptivity and lower reflectivity, so they absorb more solar energy, while metallic surfaces reflect a large portion of solar radiation due to their reflective coating, which reduces the heat absorption. Overall, the graph clearly shows that surface color significantly affects heat absorption, with darker, non-reflective surfaces heating up the most.
Based on the results, black showed the highest temperature rise with a temperature of 8.60 degrees Celsius, while white recorded the lowest temperature increase at 2.67 degrees Celsius. This clearly shows that darker surface absorb more solar radiation compared to lighter surface. These findings support Kirchhoff's law of thermal radiation, where surfaces with high absorptivity also have high emissivity. Dark colors such as black and green absorb more radiation across the visible and near-infrared spectrum, while metallic colors like silver and gold reflected most of the radiation and remained cooler. The results also agree with the Stefan-Boltzmann law, where surface reach thermal equilibrium when absorbed energy equals emitted energy. However, the main source of experimental error was the fluctuating solar intensity and environmental heat losses during outdoor measurements.
When we look at metallic surfaces, such as silver and gold, we can see that they show a lower temperature rise compared to dark non-metallic surfaces. This happens because metallic surfaces have high reflectivity and low absorptivity. In other words, they reflect most of the sunlight that hits them instead of absorbing it as heat. The reason behind this is the structure of metallic paint. Metallic paints contain tiny reflective metal flakes under a transparent colored layer. When sunlight strikes the surface, these flakes reflect the majority of solar radiation across the spectrum. Stefan-Boltzmann law states that the radiated power of a surface is proportional to the fourth power of its absolute temperature. This means that a surface will continue to heat up until the absorbed solar energy is balanced by the thermal radiation it emits, reaching what we call thermal equilibrium. Surfaces with high absorptivity like black and green absorb more solar energy and therefore reach a higher equilibrium temperature. At this point, they also radiate more heat compared to lighter surfaces. However, there are some experimental limitations that can affect the results. Solar intensity can fluctuate widely, from 232 to 1000 watt per square meter, causing variation in heating rates. Uneven heat loss through conduction, timing or reading errors, and outdoor environmental changes like wind or clouds can also influence temperature measurement.
In conclusion, this study shows that surface color and coating type play a major role in solar heat absorption. Dark, low albedo surface absorb more radiant energy and reach higher temperatures, while light color and metallic surface limited heat gain due to high reflectivity. The results are consistent with Kirchhoff's law and the Stefan-Boltzmann law, demonstrating their applicability in real outdoor conditions. Practically, this highlights the importance of using high albedo or metallic coatings in thermal management, especially in tropical climates, to reduce cooling demand and improve energy efficiency.